Within affine fixed-point systems, there is a sharp divide between what we can prove and what we can only observe. The system begins with a single symbolic branch, defined by tuple epsilon and n, spanning length h. To be viable, it must meet the expanding multiplier condition, 3 to the power of digit sum O, strictly greater than 2 to the power of length h. To move past simple observation, we need a framework that can take these parameters and determine the branch's structural properties with absolute precision. Early work in this field focused on isolated components, calculating individual endpoint closures, or constructing affine rays in a vacuum. These independent results didn't provide a way to see how the branch space would behave as a whole. The Fixed-Branch Classification Theorem unifies these fragments into a linear progression. This pipeline filters symbolic inputs through 4 successive stages: endpoint solvability, local realizability, primitivity, and enumeration. As a branch moves through these nodes, the theorem translates its symbolic properties into a final count of exact primitive families. Once a branch reaches the end of this pipeline, its structural properties are fully defined. The first node checks if an integer array can even exist for a given branch by examining its endpoint co-cycle invariance. An integer solution is possible only if the greatest common divisor of k and the multiplier difference b divides s. If unmet, the branch is impossible and analysis ends. If satisfied, the ray is confirmed, moving to local analysis. This rule acts as the first filter, removing algebraically incompatible branches. For branches that pass the first check, we look at the parameter space T. To find a valid realization, T must satisfy parity congruences, positivity and box inequalities, and specific floor quotient conditions. The inequalities establish a rigid lower bound, invalidating values below a certain point. Then parity congruences act as a sieve, selecting only evenly spaced discrete points. Because each local constraint contributes a single lower threshold or congruence refinement, the result is predictable. The intersection always forms an eventual arithmetic progression, a starting point, T start, plus a regular shift, Qj. These complex local requirements consistently reduce to a simple, structured progression. The third node distinguishes between primitive symbolic words and proper powers, words that are simply repetitions of a shorter root. If a word is a proper power of a root v, it inherits its admissibility. Repeating the sequence to create a longer word doesn't change the underlying properties. Therefore, the realization sets for the repeated word and its root are exactly the same. This principle shows that symbolic repetition generates no genuinely new orbit families, keeping the dynamic space entirely manageable and contained. The final stage converts these structural findings into an exact numerical count. We start with the total set of admissible necklaces at length h, labeled A sub h. This total count includes primitive necklaces and their repetitions. We must isolate the primitive necklaces of exact period h, P sub h. The Möbius primitive decomposition formula extracts the subset, using admissible counts across divisors to pinpoint the exact number of primitive families. This method of calculation has been confirmed through independent computational modeling. By reaching this final node, we have moved from a raw symbolic string to a precise count of every primitive family the branch can produce. At any fixed branch length, the pipeline is effective. It gives us a complete description of the admissible families without leaving any variables unresolved. However, this certainty is tied to fixed parameters. When we try to look at all possible lengths simultaneously, the volume of data grows rapidly. We end up with a massive union of all primitive sequences across every possible length. While we have total control over a single branch, we lack a framework to describe the behavior of this combined global set. The next challenge is finding a way to establish uniform control over all branches at once. There is a significant gap between bounding a single realization set and bounding the growth of the primitive sequence as length h approaches infinity. We are now searching for a unifying mathematical principle that can definitively constrain the growth of this infinite sequence. The fixed branch is now a solved problem, but finding a unifying rule for the simultaneous union of all branches remains an open question in dynamical systems.